Hi. In the last section, we talked about quadratic functions. Those were polynomial functions, and they involved x to the second power, but no higher power than that. If we involved x to the third power, or the fourth power, or the fifth power, or something like that, then we'd have a polynomial function of higher degree. So today we're going to talk about polynomial functions in general and what we can expect from them in terms of their graph or their formula and what we can say about them. To start with, to get you used to thinking about what polynomials are, here are some examples to look at. 5 examples of polynomial functions. The one in the middle here is a quadratic function, but it counts as a polynomial function. And then these others are also examples of polynomial functions. And what they all have in common is that they are made up of several terms added together, where each one of those terms is either just a number, a constant term like 12 or 125, or it's a number times x to some whole number power, like -3 times x to the 2 power, or 24 times x to the 1 power, or 1 times x to the 3 power. So that's basically what a polynomial is. It's made up of one or more terms added together, where each term has a numerical coefficient times x, or whatever the variable is, to some whole number power, or just a number by itself, which would be a constant term. Now here are some examples of functions, let me go back there. Functions that are not polynomials. They're still functions, they're perfectly good functions, they're just not polynomial functions. X over x squared minus 9. You can't be dividing by something involving x in a polynomial. Square root of x plus 3. If you're taking the square root of something involving x, it's not a polynomial. 4 minus x to the 2/5 power. You can't have a fractional power of the variable in a polynomial. The absolute value of x minus 1 minus 4. Once you take the absolute value of x minus 1, it's no longer a polynomial. And our old friend, the greatest integer function. It's a function, but it's not a polynomial function. So in general, here's the general definition of a polynomial function by showing you the pattern that it has to fit. So these a's with the different subscripts just stand for any real numbers. You have any number times x to the n power, plus any number times x to the n minus 1 power, plus all the way down to any number by itself. That's a polynomial function of the variable x with degree n. So by the degree, we mean that's the highest power that x is raised to. And then another vocabulary term that you may need to know, the leading coefficient of a polynomial is the coefficient, that is the number that's multiplied by that highest power of x. Now usually the terms are written in order from highest to lowest powers of x. So if it is written that way, the leading coefficient is the coefficient on that first term. But even if the terms are written in a different order, still the degree is the highest power that the variable is raised to, and the leading coefficient is the coefficient on that highest power of x. Now let me just mention that we're only going to be studying polynomials that involve one variable at a time. You can have polynomials that involve more than one variable, like a polynomial in x and y, and then the definition of the degree is a little more complicated, but we're not going to be worrying about that. So going back to our examples of polynomials, this polynomial has degree 3. because you've got x to the 3 power here, but no higher power, and the leading coefficient is 1. Here the degree is 4. The leading coefficient would be -1. In this polynomial, the degree is 2. What about this one? The degree of this polynomial is 6. And for this polynomial, the degree would be 5. And that's going to be important because if you know the degree of a polynomial, you know something about how complicated the graph can get, how many zeros the polynomial can have when we talk about those in a few minutes here, things like that. The simplest possible polynomial of any particular degree would just be x to that power just by itself. That counts as a polynomial. So if we just had y equals x to the 6th power, that would count as a degree 6 polynomial. It would be the simplest degree 6 polynomial that you could have. So these are what the graphs of those really simple polynomials look like. Then any other degree 6 polynomial, the graph might look kind of like this, might be flipped upside down, might be stretched or squished, might be shifted up or down or right or left, and it might have some more wiggles in the middle. But notice that when we have the odd powers of x, that is an odd function. If you remember when we talked about odd functions and even functions. And for x to the 1st power, that's just a straight line. For x to the 3rd power, that's the cubing function that we've seen before. For the x to the 5th power, that's sort of like x to the 3rd power, but flatter in the middle, and then it goes up faster when you go away from the middle. And then here are some even powers of x. X squared is our old friend, the squaring function. The graph is a parabola. X to the 4th looks sort of like a parabola, but I got this mislabeled. X to the 4th is the purple one, and x to the 6th is the green one. They look sort of like parabolas, but they're more flat in the middle. And then they go up more steeply as you get away from the middle. Here are some more polynomial functions and their graphs. So a degree 1 polynomial that just involves x to the 1st power, that's a linear function. The graph is just a straight line. A degree 2 polynomial function, that's a quadratic function. The graph is a parabola. We've studied those. A 3rd degree polynomial function, well, here's one example of that. Notice the graph has 2 turning points. The parabola just had 1 turning point. The degree 3 equation, the graph has 2 turning points. For this degree 4 polynomial, the graph has 3 turning points. The degree 5 polynomial, the graph has 4 turning points. And the degree 6 polynomial, the graph has 5 turning points. Now, some degree 6 polynomials don't have that many. Some don't have 5 turning points, they have less than that, but they're never going to have any more than that. So the degree of a polynomial tells you how wiggly the graph can get, how many turning points at most it can have. That would be 1 less than the degree. And then it also tells you how many times the graph could cross the x-axis, how many x-intercepts it could have. So the maximum number of x-intercepts is the degree. Degree 6, you could have as many as 6 x-intercepts. Degree 2, you could have 2. You might not have any, but 2 is the most you could have. So here's what you can say about the graph of any polynomial function. Here are some things that are true about any graphs of polynomial functions that are not necessarily true about other kinds of functions. If you're looking at the graph of a polynomial, it is going to be continuous. That means that the graph is all in one piece, connected. There are no gaps or holes or jumps. Also, the graph is going to be smooth. There are no sharp corners, no abrupt changes in direction. And it is going to be curved. As long as the degree is greater than 1, so you're not just talking about a linear function, there will never be any part of the graph that is a completely straight line. It might look fairly straight, but if you zoom in enough, you'll always be able to see that it's at least a little bit curved on every part of the graph. And like I was talking about, the number of x-intercepts of the graph is the degree of the polynomial or less. So if the degree is 4, you might have 4 x-intercepts, or you might have less than that, but never any more than that. And the number of turning points is the degree minus 1 or less. So if the degree is 4, you could have 3 turning points, 4 minus 1 is 3, or you could have less than that, but you can't have any more than 3 turning points for a degree 4 polynomial. And if you have an even degree polynomial, it's going to be going either up both ways as you go off to the right and as you go off to the left, or it's going to be going down both ways. Which one of those it is depends on whether the leading coefficient is positive or negative. So the example we're looking at here, with a positive leading coefficient and an even degree, the graph goes up both ways. If it were negative 2x to the 4th plus some other stuff, then it would be sort of like this, only upside down. It would be going down to the right and to the left. That's if it's an even degree polynomial. If it's an odd degree polynomial, then it's going to be going opposite ways as you go to the right and to the left. There, as you go off to the right, you're going to be going up if the leading coefficient is positive, and down if that leading coefficient is negative. And then the opposite direction as you go off to the left. So remember our non-polynomials. Some of them were not continuous or connected. They had graphs that were in more than one piece. Some of them had sharp corners on the graph. Some of them had graphs that didn't go all the way to the left or to the right. But none of those things happen with polynomials. For graphs of polynomials, they are smooth with no sharp corners. They are connected all in one piece with no gaps or holes or breaks. And notice degree 3 goes up to the right, down to the left. Degree 4 with a negative leading coefficient, down to the right and down to the left. Degree 2 with a negative leading coefficient, down to the right and down to the left. Degree 6, that's an even degree with a positive leading coefficient, up to the right, up to the left. Degree 5, that's an odd degree with a positive leading coefficient, up to the right and down to the left. So this kind of summarizes the possibilities for whether you go up or down as you go to the right or to the left. When you have an odd degree, it might be wiggly in the middle, but eventually goes up to the right and down to the left if the leading coefficient is positive, down to the right and up to the left if the leading coefficient is negative. When the degree is even, it eventually goes up to the right and up to the left if the leading coefficient is positive, down to the right and down to the left if the leading coefficient is negative.